Welcome back to the second part of experiment 4. In this part we will talk about the Fmd modulation process. I have already built the demodulator circuit for the purpose of explaining. So let's talk about the demodulation process. Let me just bring out my sketchbook. So in the last section we have built this whole part. This was our modulator circuit, and this circuit over here is our demodulator circuit. It has very basic three components. The first one is a product modulator. The first one is a product block. It just multiplies two signals. A Butterworth filter. We have already used this in previous experiments. And a new component here is continuous time VCO. So what is continuous time VCO? Let's talk about this first. So VCO basically stands for voltage controlled oscillator. So this block creates an oscillation based on a given voltage. So whatever voltage is given here, this voltage will create an oscillation or a sine wave or cos wave like signal depending on this voltage. So let's see how this thing will work. So firstly, there are two inputs to this product block. The first input is this one, this FM wave, and the second input is the output from the continuous time VCO. Now, continuous time VCO also has a output signal having same or similar type of equation. Let's say the output signal is VT. For the sake of our mathematical analysis, let's say VT is this output. VT will also have similar shape. It will have amplitude A. It will be sine or cos depending on the our phase shift. So let's say it's a cos wave. Then instead of it, it will have a frequency. Let's call it f2 by f naught t, and then it will have a similar type of equation like this. It will have, let's say, another kv, and then again another this type of thing. This v tau is the input here. Let's say that's v1 tau. The input here is v1 tau. So it will have a similar type of equation like this one. There are a whole lot of similarity. So we call this f0 free running frequency. Free running frequency. And we tune this f0 to fc. We keep this same. So we choose f0 such that f0 is equal to fc. And we choose this kv. Kv is the factor here. So we choose this kv such that kv is equal to kf by 2 pi, because this this block is by default multiplied by 2 pi. So when it will be multiplied by 2 pi again, it will create kf. So we choose kv to be kf by 2 pi, and this kf by 2 pi is multiplied in this block by 2 pi itself, so it will result in kf. So we initially put kf by 2 pi here. Kf is again this value. So if this value is 10, we will put this kv as 10 by 2 pi here. So what's the big deal? Let's erase the unnecessary portions. So we have already said that we will tune this to FCT. So there are two cos waves basically. This one is one cos wave and this is another cos wave. So when we will product these two, let's say we are producting cos A and cos B. In this case, we will have two cos waves like this, cos A plus B and cos A minus B. So we will basically, in one cos wave we will add these two frequencies, and in another cos wave we will subtract these two. So there will be two frequencies. One frequency will be A plus B, or in that case you will have 4 pi FCT plus another thing coming from the addition of these two. This is one frequency, A plus B, and for A minus B, you can see these both frequencies have this common. So when we subtract, this will be cancelled out. So we will have something else. Let's say another box. In this box we have this frequency minus this frequency, or this frequency minus this frequency, but this FC frequency terms are cancelled out. Now when we will choose the cutoff frequency of this bandpass or this low pass filter in such a way that it will only pass the low frequency components, then this frequency will not be passed, because there is a FC component here and it will be blocked. So only the component that has a difference between these two frequencies will be passed. And this continuous time VCO will take some time, and in some time it will create this output to be equal to our message. So it will take some time. After some time you will see that this output here, or the input to VCO, the output of Butterworth filter is actually the input to VCO. This signal will become equal to our message, or it will have the similar shape of our message. It will not have the exactly same amplitude, but the frequency will be exactly the same, but the amplitude will be different. It will take some time, but after some time it will achieve our desired result. So at last we have a gain block. As I said, the amplitude will not be the same as the message signal. It will have lost some of its strength. So to put that strength back, we will have a gain component here, and finally it is going to the scope. So let's see what we can see in the scope. Okay, so now let's run the simulation and check out if our output is working. So let's just remove the FM modulator signal first. Let's just remove this for time being. Let us check the input signal and the output of the demodulator. This should be same. So let's see. Okay. So as you can see, there are three signals. The red one is obviously we haven't connected anything to the third port, so it's just a empty signal. Just concentrate on the yellow and the blue ones. So the yellow one is the input, and the blue one is the output of the demodulator. Now, as I have said, the VCO will take some time to adjust the output signal to the input, because it will take some time to actually produce the result so that it is in a perfect balance. This condition is called phase lock condition, and the method is called phase lock loop method of demodulating FM signal. So as you can see here, the blue signal is not equal to the input signal straight away. It's taking some time, and it's normal because the VCO will take some time to adjust, because it's a feedback system and it will not work instantly. It will take some time actually to set the output voltage equal to the input. Originally, the amplitude of the blue signal would be much less than what it is now. We have used an external gain block to actually boost the signal. If I just remove the gain, you would see that this blue signal will not be as high as it is now. It will be something lower than this. But anyways, we will use the gain block to boost the output of the signal. Now, let's check back the whole three signals together and see if it's working. Now I'm just joining the third port to the FM wave again. Okay, let's start. Now let's just simulate it again. Okay, so it's not something very pleasant to watch. Let's just zoom it in. Let's zoom this portion for a better view. Okay, so as you can see here, the red one is the FM signal. You can see when the input signal or the yellow signal is having a high value, the frequency is very high and the signal is very dense, and when the value of the input yellow signal is very low, then the red signal, which is the FM signal, is very loosen up and it's the low frequency region, and the blue signal is exactly like the input signal. So I have used the gain as 10 here. I have done it by doing some trial and error. You can do your own. You can even set it to let's say you can choose 11 here, it will produce a better result. So let's see. No, for 11, let's just zoom it here. Let's just zoom this portion. So for 11, you see it's a bit overcompensated, and now the blue or the output signal is higher than the input signal. So it's something between 10 and 11. You can keep it as 10 if you want. So that's all for FM modulator and demodulator. The new block here is continuous time VCO. You can just choose it by searching VCO here. If you search for VCO, then this block is continuous time VCO block, and you can just drag it in. So once again, in short, what does continuous time VCO do? It is an oscillator. It creates an oscillation based on the input. It has two frequencies. One is free running frequency, another one is actually another one depends on the input signal. If I just show you the block, there are 4 parameters. The first one is output amplitude. I have just kept it 1. It is the free running frequency, and I have chosen it 20, as I have said. It will be tuned to the FC. So I have chosen it 20. And sensitivity, as I said, the sensitivity is the factor or the coefficient of the message of the input. So I have chosen it 10 by 2 pi because it is 10 here, and it will by default multiply it with 2 pi. So I have intentionally divided 2 pi so that the whole result will be equal to that 10. And the initial phase, I have chosen the cos wave, so I have put a pi by 2 here. So it's done. So this continuous time VCO will create a signal similar to this fashion, as I have chosen the free running frequency to FC. So this part will be exactly same, and here the change will be the m tau. It is m tau for ST, and for continuous time VCO, in the place of this m tau, it will be this signal, the signal that is coming out from the Butterworth field. It's the input signal. So the continuous time VCO will try to make a balance, and in the process of making balance, it will create this signal to be equal to m tau, so that it reaches the perfect balance. So it will take some time to reach the balance. Initially, output of the signal here will not be equal to the message, but after some time, as some time will pass, it will eventually reach that capture phase, and the voltage here will be just equal to the message signal. So that's all for FM modulator and demodulator. In the report section, you will have to obviously simulate this one. Of course, you have to simulate this one. Additionally, there are built-in blocks for FM modulation and demodulation in Simulink. You can just search it by FM modulator. You can see there are FM passband and baseband. You will just choose passband modulator. So there are FM demodulator block as well. You will use this FM modulator and demodulator block to achieve the same result. That is the task in the report. So I hope you will be able to do that, because it is very easier compared to this whole circuit. Another thing that I want you to do is dig a bit more in for the continuous time VCO. Just include a paragraph on what the continuous time VCO is doing based on your understanding of this video, and you can just search it in Google, or you can fetch some ideas from internet and just write a paragraph on what this continuous time VCO is doing. You don't need to write any detailed equation as I have written in this video. You just need to get the idea what this continuous time VCO is doing. That's all. So that's all for this 4th experiment. We will discuss more in the live session. Till then, goodbye.